just want to welcome everybody to our August Tech Talk. I'm absolutely delighted to have Yegi Bonyadi from Lyra Electronics join us today. And before I introduce Yegi, I just want to maybe give you a quick background of AESIN for those who don't know who AESIN is. And then we can move to the talk. So AESIN is the Automotive Electronic Systems Innovation Network, established 12 years ago to bolster UK's position as an innovation lead for electronics. We've been operating now for 12 years. We've had our 10th conference anniversary last year. We've just finished our 11th conference this year in July, and we hosted that at the British Motor Museum in Gaydon, which was a resounding success. So we're absolutely delighted that we can be working with some of the smartest minds in the UK when it comes to automotive electronics. The way we're structured, we have a number of interest groups around which our members converge to talk about important topics. And right now, one of the most interesting groups we're starting off, pertinent to you all on the call today, is around power electronics and control systems. And that we're keen because there's a lot of interest around the development of power electronics as a community, as a capability in the UK. And we want to see what we can do to develop that through our network. With that, it's a nice little link in now to our talk. So Yegi joins us from Lyra Electronics, as I've said. And Yegi is an electronics team lead at Lyra and has a Ph.D. from the University of Warwick, which is very dear to my heart because I spent over 15 years at Warwick University and became good friends with Professor 𝗧𝗹𝗯𝗵, who I believe was Yegi's supervisor, who's an absolute genius in this area. So Yegi's work is around the design of high-power DC to DC converters, onboard chargers, and cost-effective design, EMC design. And that's where a lot of our interest lies, and especially around wide bandgap semiconductor devices. So I'm going to hand over to Yegi in a second. What I'll ask you to do is, if there are questions, please pop them in the chat. And at the end of the talk, then I'll pick up a few of the pertinent questions and we'll then pose them to Yegi to answer. So with that, Yegi, the stage is all yours, and thank you very much for taking the show today.
Thank you very much, Connie. So hello everyone. I'll just start sharing my screen. Yeah. I hope you can see. I hope you can see that now. So yeah, I'm Yegi. I'm from Lyra Electronics, and today I'll just give you a talk about EMC design techniques for high-power DC-DC converters, mainly the ones with silicon carbide MOSFETs in them. Just before starting, I'll give you a little bit of background about myself and Lyra Electronics, and then I'll present to you the case study that I want to talk about today. So as Gani mentioned, I'm the principal engineer and electronics team lead at Lyra. We focus on power design for power electronics for automotive application and marines, medical, and any other application that needs power electronics. But my main interest is DC-DC converters, onboard chargers, and cost-effective EMC design. At Lyra, we do everything from simulation, prototype design, test and validation, and we've got teams including electronics, mechanical, software, system, test, and validation. And we have recently got our own EMC and environmental test facility, where you can see the picture of in this slide. So we do have our own capability to test conducted and radiated emissions at Lyra. This is a 𝗧𝗹𝗪25 semi-anechoic chamber. The dimension, it's around 6 by 6 meter wide, and also we can also do environmental testing, where we've got dynamic climate chamber, and we've got a humidity control as well. So in this test facility, we can test and validate for power electronics for automotive, off-highway, marine, aerospace, and not only for Lyra, but also we do offer this as a service for external customers as well. So if you have any interest in this, please get in touch. So now I'll just get on with the topic of this talk, which is the automotive DC-DC converter. So I'll talk about how a 𝗧𝗹𝗸 testing method is, what conducted emission test setup should look like, and I'll show you some of Lyra's test setup and how we troubleshooted our EMC issues, how we find sources of EMI, and what techniques to use to improve the results. And at the end, I'll show you how the emissions were improved and how we passed our EMC test. So this is showing you a little schematic of a dual active bridge DC-DC converter. In electric vehicles, they use two different power systems, a high voltage battery, which you can see on this side. And in this case, it can either be 800 volts or 400 volts, and also a low voltage battery where supplies all the electric appliances in the car. In this case, we've got a 24 volts or 12 volts version of this. So on the low voltage side, we can have something between 150 amps to 300 amps. So it's quite high current. And the DC-DC converter that I'm going to talk about is 4 kilowatt rated and uses silicon carbide MOSFETs in the high voltage side here. So as you know about silicon carbide, they do have large dV by dt and di by dt events, which causes high electric and magnetic field, which are both sources of EMI. And if you're relying on having Y capacitance just to solve your EMC issues, I think it's time to review your design, because every time you double your voltage, the available Y capacitance is reduced by 75%. So it's important to think about EMC and not just rely on Y capacitance. For this converter, we had to comply with 𝗧𝗹𝗸 automotive EMC standard, which I will talk to you about it in the coming slides. So as I mentioned, EMI is quite important. It can no longer be an afterthought. So it's got a potential to cause significant setbacks later in the design that can cost both time and money. So always think about EMC from the beginning, from PCB design stage where you're selecting your components, have EMI in mind. If you're placing components in the PCB, you have to have EMI in mind. Identify your di by dt and dv by dt circuits and nodes, and minimize the surface areas for these components. And also need to be really careful about your PCB layout. If you've got cables, bear in mind that cables can radiate, and conductor path through cabling is quite important. And also knowing how to design filters to be effective in the frequency range that you're interested in is quite important. As I mentioned, 𝗧𝗹𝗸 is what we had to test to, and you can see on the diagram down below, the conducted and radiated emission tests have different frequencies that you need to test them in. So for conducted emission tests, the range is from 150 kilohertz all the way to 108 megahertz, and radiated emission test goes from 30 meg all the way to gigahertz. So 𝗧𝗹𝗸 testing method provides you with defines two methods. One is using a current probe, and the other one voltage method. So both of them can be used. It depends on your OEM requirements. If they want to use the current method or voltage method, they will need to let you know. But in the table that I'm showing here, it shows you the 𝗧𝗹𝗸 passing limit at different frequencies for voltage method in the middle column, and also the current probe method on the right-hand side column. The limits given for voltage method are from 𝗧𝗹𝗸 standard, whereas the limits for the current probe method are converted from 𝗧𝗹𝗸 standard units. So they're converted from dB microamp to dB microvolt for comparison. So you can see what the comparison between using these methods are. So here I'm showing you the EMC test setup for conducted emissions based on 𝗧𝗹𝗸. On the right left-hand side of the slide, there are two pictures. They show you how you need to set up your test, how the device on the test should be placed. You can see the big ground plane here, and how the device has to be placed on a low relative permittivity support, which is around 5 centimeters, and then it has to be bonded to the ground plane, the same as your 𝗧𝗹𝗸s and the power supplies. The length of the cables are quite important, so always refer to the standard for these. And before, because we didn't have our, we've just got our EMC test facility, but before getting those, we had set up this little conducted emission test setup at Lyra, where we did some of our tests for this project. This was around a year ago. You can see the ground plane, the device on the test, the 𝗧𝗹𝗸s. This one is the high voltage 𝗧𝗹𝗸 and the low voltage one as well. And the length of the cables and how they should be placed is also based on the standard. The 𝗧𝗹𝗸25 standard also shows you the test setup that you need for radiated emissions. So again, it shows you how we need to place the antenna, what position the antenna should be, what's the distance between the cables to the antenna, and how the cables should run from the device all the way to your measurement. So these are quite important to have that in mind. And if you're setting your test in your lab, just make sure that you do set them up according to these test standards. Okay, so spectrum analyzers are normally used to measure the emissions, but they cannot distinguish between common mode noise and differential mode noise. In this slide, I'm showing you the difference if you use a discrimination network between your 𝗧𝗹𝗸 and the spectrum analyzer. You can separate common mode from differential mode noise. So in the graph on the right-hand side, you can see how this is shown, and it does help a lot when you're trying to troubleshoot your device. If you're failing, for example, in this case, if you're failing between, let's say, 80 to 100 megahertz, and you can just separate them to know if it's more common mode noise or differential mode noise, and then design your filters according to that. As I mentioned, you can also use current probe for doing your troubleshooting and testing. Both current probe and using a 𝗧𝗹𝗸, they show very similar results in low frequency, but in higher frequency above 5 megahertz, there can be some differences. And there are a few possible explanations to explain why these differences are. The first one would be that the current probe position is quite important. In 𝗧𝗹𝗸25 standard, they specify 2 locations where you should place your current probe. One is 50 millimeter away from the unit, and the other one is 750 millimeters away. So by placing the current probe at different distances from the device, certain harmonics become more apparent at specific locations. So that can be an explanation why you would see different results compared to 𝗧𝗹𝗸. And also the diameter of the aperture of the current probe is quite important. If you use smaller aperture, the more it will be more efficient. The coupling will be more efficient. If you have a current probe with a larger aperture, they're optimized either for low or high frequency coupling efficiency. So these can be just the explanation as to why you see some differences. As you can see here on this graph on the right-hand side, 𝗧𝗹𝗸 measurement and current probe measurement, you know that the trend is the same, similar, but you've got a bit of differences in high frequency range. And this is also again showing the same thing, but I'm showing you from 150 kilohertz the spectrum, and this is the conducted emission test result from 150 kilohertz all the way to 100 meg. And you can see below 20-30 meg, it is almost the same, similar, but above that, there are some differences between using these 2 methods. Okay, so now these are the results of the first emission, the conducted emission results that we got from testing our DC-DC converter. Just to let you know that we have to test according to 𝗧𝗹𝗸25. You have to test every cable coming out of your device. In our case, there is one high voltage cable, which was the 400 and 800 volt